Okay, so let's get started. So I sent some material the other day on something which probably would help you with the programming part, and also some references for the calculus part. I hope you guys have found this useful, and I hope you have started trying out some coding exercises. So sometime in the probably end of this week or next week, early next week, you will get your first assignment. So that will primarily be on the preliminaries part. So linear algebra, calculus, and some things that I'm going to teach today on the real analysis part. Okay, so just a heads up. Okay. All right, so any concerns, any questions so far till date? Anything that's bothering you or Is everything going fine with the course? It's comfortable for you all?
Oh, ma'am, I had a question.
Yes.
Ma'am, for the prerequisites, the preliminaries, how much do we go in depth while studying it? So, like, sometimes when you mention things, it becomes like a nagging thing that you have to check the proof and understand the proof. So, I just want to know that for the preliminaries, how much do we actually have to recall in depth? Like, we could sit and do linear algebra for 2 days, but would that be required?
So so whatever I've done in class is to the extent of how much those things will keep coming up. Okay, you will need to recall some of these concepts. Okay, so those are the things that I've just touched upon in the class. So things like you should be comfortable with knowing stuff like when a system of equations has a solution and how to detect it doesn't have a solution, and how to find out all the solutions, those kind of things. And even like eigenvalues, I mean, you should understand like why you compute it in some particular way and stuff. I mean, the reason is that you're going to be using these later in the course. So at that point, you can still go back and refer, but you should just generally be comfortable using all these concepts. Okay, so the problem, like I gave out some of the practice questions, right? So I think if you see that, you'll get a sense of how much you need to know. I mean, so it's along that lines. That's the kind of comfort level you should have in linear algebra. Okay, so yeah, similarly for calculus and even real analysis. So yeah, so does that answer your question? It's clear?
Yes, ma'am. Yes, ma'am. Thank you.
Okay. All right. So, yeah. Anything else? Anybody else wanted to ask anything? Any concerns? Okay. So, I think you guys are okay now. All right. So let me continue with the calculus primer. Just share the screen. Okay. So it should be visible now, right? Screen is visible.
Yes, ma'am.
Okay, good. So, so recall in the last class, we were looking at some preliminaries in calculus. So we stopped at these O notations, right? Like we saw different notions, the small o and the big O. And you also saw some of the situations. It could come in algorithms, you say in some way, and in math, it comes in another way. But the unifying thing behind all this is you take limit around some point. Okay, and that point is necessary to mention. So now with this O notations things in place, let's move on to this Taylor series approximation. So this is going to come repeatedly in optimization because many functions you don't know what happens later on, and you want to see how the behavior is. So that's around a local point. So that's when you go for this Taylor series approximation. So did someone try to join or? I think it's okay. I just thought I got a notification. Anyway, so Yeah, so that's the Taylor series approximation tries to approximate the function around some point. It's trying to capture some local behavior. So suppose you have a function which is can differentiate it any number of times. The differential exists. So at x equals x0. So then the Taylor series approximation around the point x naught is this expression, right? So f of x naught plus some h. So a small step in the direction of h. Okay, that is going to give you an expansion of this form. So you take f of x naught, then you take h times the derivative at x naught, then you take the second derivative times h square and so on. Okay, so it makes use of all the derivative information at x naught. Okay, so this is an exact representation of the function value at the point x naught plus h. Okay, so yeah, so this is, I'm just explaining it now for a function which is from R to R. Okay, the simple case. So so now the Taylor series expansion looks at what happens when h becomes very small. So that means at a point very close to x naught, what can you say about the function value? Okay, so now many times you don't want to go, I mean, it's an infinite expansion. So, how much do you go? And, what is the loss if you truncate it at some point? Okay, so if you use the first m terms, okay, so you could use the first m derivatives. Okay, so that is going to give you something like this, right? F of x naught plus h times f dash plus so on, plus the nth derivative will give you this term, h power m times f m. So this is the m derivative by m factorial. And all the rest of the terms, okay, that arise in the infinite summation, that you can just compress it with this O notation. This is small o. Okay, so what it means is that, yeah, it's an approximation for the rest of them is h of m. Okay, so this is an this function that you have here is very small compared to h of m, h power m, sorry. Okay, the whatever function, the rest of the terms here, that is very small compared to h power m. Okay, so in some sense it is negligible. Okay, so remember O notation said that limit, so you had like limit, so what was it, f of x by, we call it something else, so g of x by h of x. Okay, so this is around the point x goes to 0. So this is very small, right? That's when you say g of x is O of h of x. So that's what this means. To around the point h is 0, this term, the rest of the terms become negligible. Okay, that's what this means. Okay, so now what you can do, since that's the case, you can use different derivatives. For different values of m, you're going to get different right-hand sides. So if you take the first order approximation, that means you're just using the first derivative. So then you will get f of x naught plus h times f dash. Okay, so this is one approximation. Okay, now it's not an exact expansion of f of x naught h plus h, of course, because you are neglecting many higher order terms. But this is right to say it's an approximation. Okay, now if you use the second derivative as well, you stop at this point. Okay, so this will give you a better approximation than the first order approximation, and you can keep doing this. Okay, so as you include more derivatives, you get better and better. The approximation becomes better and better, but there's more effort in terms of including more terms and stuff. So now the 0th order approximation is just nothing but f of x naught. So you're not making use of any other derivatives. So that is what you mean by 0th order. So the 0th order approximation is just f of x naught plus h is f of x naught. So this is an approximation. So you can see, that this is going to be a very bad approximation, right? Because just approximating with the point value there. Okay, so let's take an example for this. I mean, yeah, we'll also see what these functions look like. So I'm just looking at this function x e power x. Okay, and let's say x naught is 2. So around the point 2, I'm trying to see what the function, how the function looks like. So now let me try to construct these zeroth first and second order approximations. So the zeroth order approximation is just going to be f of x naught. So f of x naught is what? 2 e power 2. Right? It's just substituting the value of x naught in f of x. Now, if you look at the gradient, so what are things you need to do to find the first order approximation? You have to find the gradient. So let's do that. The gradient is just, you just take the gradient here. So it's x e power x plus e power x. So I use the product rule here. And at the point x naught, that is also something you need, right? You need this term. So f dash of evaluated at the point x naught. So then you'll get this 2 e power e square plus e square. Okay. Now similarly, the second derivative. So you need to you take the derivative of this f dash x, and what you're going to get is just x e power x plus 2 e power x. Okay. And evaluated at x naught, you're going to get 4 e square. Okay. So let's just try to write the approximations. So now, can somebody tell me what's the first order approximation? So remember, you just need to plug in these values, f of x naught plus h. Okay, so it's just f of x naught plus h times f prime. So can somebody tell me? What's happening? Okay, are you all here?
Yes, ma'am. 2a square.
Yes, ma'am.
Yes, okay. So somebody was answering. Can you tell me? Okay, someone started answering, so please come forward. 2e square, so that is f of x naught. So that's this value. So that is 2e square plus
h times 3 square.
h times 3 square, right? Okay, so that's how you would write. So you can see that this is a linear function. So this is a function of h, and it's linear in h. Okay. Now similarly, if you take the second order approximation, so I think I wrote it down here, but anyway, let's have some of you try it out. The second order approximation, can you tell me?
The above.
This one, yes, h times 3 square plus
H square by 2, 4 e square. Or h square, 2 e square.
Yeah, 2 e square, 2h square e square, right?
Yes.
Okay, so this is, you can see this is a term. H is the thing that changes, right? X naught is a fixed quantity and h varies. So this at this point you're going to get a quadratic term. So you have an h and an h square. Okay, so yeah. So I'll just show you, like just to give you a sense of what these functions are going to look like. So I've just implemented this on MATLAB. So I've just taken the range between -5 to 5, and I've evaluated the function. So that's x e power x. Then I've evaluated the zero order. Okay, so that is just nothing but the function value itself. Okay, at the point x. Okay, so this is the function approximated around the point x is x naught is x. Okay, so now, so Taylor series of 1, the first order also I've just scored up. So just, whatever you just saw now. So I've just evaluated these and the gradient as well. Okay, okay. So let's just see this. Okay, so I'll just plot the function itself. Okay, so this is going to be the function. Let me just keep this on top. So this is the function x e power x. Okay. Now let me plot the first order approximation. So remember that was a linear function. So this red curve that you got, So this red curve that you see here, that is the first order approximation. So this is the point x is 2. And you can see that around that, it's a reasonable approximation, around very close to x equals 2. Okay. Now, let me plot the second order approximation. So remember that was a quadratic function, and that's what you see here. Okay. So it just gets a little better. The region at which it is a good approximation, that is a little better. Now I've also plotted the third. I've also computed the third order approximation. So that is something like this, right? So that you're going to have some h cube terms. Again, that's the one which dominates, and so that's how it looks. So you can see all the different approximations here. Okay, so this you could keep going on and on, as with the higher order as well. Okay, so turns out that these functions, these approximations, will be used later on, like when you try to build some optimization algorithms. The usual way to approach it is through these Taylor series approximations. Okay, so now, yeah, so you should try this for some other functions too, and just to get comfortable with this Taylor series approximations. Now, what you saw so far was functions R to R. So you could also do this for multivariable functions like Rn to R. Okay, so it's just the same thing. You just take the gradient here instead of f dash. Okay, and it's just going to have this x minus x naught transpose del f. Okay, so f of x. So earlier you had, this was actually the x naught plus h that we had. Okay, so it's just the same thing. It's just generalized to more dimensions. And similarly, the second order approximation is going to give you something of this form. And here you are going to use the Hessian. Okay, so the Hessian information at x naught. Okay. So yeah, so this completes the calculus primer that I wanted to share with you all. Okay, so any questions so far? Is everything clear?
Yes, ma'am.
Okay. Rohit, it's clear. So what about everybody else? You can type in the chat box. It's clear. Okay. Clear. Okay. Good. 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 It's clear. Okay. Okay. Okay, thanks, everyone. So are there any fourth year BTechs here who have responded? Any fourth year CS BTech? So I don't hear from you guys. I don't know what's happening. So I hope it's clear to you guys as well. All right. So, okay. So now let's, the some preliminaries that I wanted to explain to you guys. So the other thing is about topology or real analysis. So have you done a course on real analysis?
No, ma'am.
You haven't done a course. Okay. So Harsimran, you are a master's student or are you an undergrad?
Master's.
Master's student. Okay. Sure. So you haven't done. So I think this would be useful to get. So what about the undergrads? Did you have any course on real analysis here once after you joined?
No, ma'am.
You didn't have. Okay. Okay. So it turns out that this is also something that you would require at many points in the course. So let's just get into this. So we already saw limits, right? And some things about limit of a function. So now what about sequences? So if you're given a sequence of this sort, x1, x2, and so on. So when do you say it converges to x? Okay. So you would say so if as n tends to infinity, the limit of the sequence that is the point X. So that's when you say that a sequence converges to X. Okay, so it's just a very similar notion, just instead of a function, you're saying a limit of a sequence. Okay, so to capture this mathematically, what you'd say is that for all epsilon, there is some n. Okay, so this n goes to infinity comes, so that's where you say there is some large capital N, such that whenever this n is greater than this capital N, xn, the point in the sequence, is within epsilon of this x. Okay, so it's just as you go to the end of the sequence, there's really no end because it's infinity, but as you go further and further, you will be close to x. That's what this means. So to understand this, just an example, like if you're traveling from Goa to Mumbai, so and you are computing the distance remaining to Mumbai at any time t. Okay, so maybe the sequence would look like something like this. You start off with a large distance and it goes on reducing. Okay, and at some point you reach Goa, and that's when you have like values very close to 0. Okay, so this means the sequence converges to 0. So the distance remaining to Mumbai, that is going to converge to 0, assuming that you are making progress, that you are going towards Mumbai. Okay, so that's just to give you an intuitive feel for what you mean by a sequence and its limit. Okay, now there's this notion of sphere or neighborhood or a wall around a point x0. So what this means is it's just a set of all points which are at a distance of r from x0. Okay, so here usually the norm that you use here is the 2 norm. Okay, so what would it look like? So the 2 norm, we know that it is it's like it's a Euclidean distance after all. Okay, so what it would be, so you would have something like, so let me take it in 2 dimensions. So you'll get something like x1 minus x0. So this is the first coordinate of x. Okay, let me just write it in a better way. x1, this is the first coordinate of the point x, and so this is okay, so this square plus x2 minus x0, the second coordinate. Okay, this value is going to be less than r square. This is also the same thing. So you can see that this is just the equation of a circle, right? So just move this down. Okay, so yeah, so what you're going to have is so you have the point x here, and every other point. Okay, my drawing is very bad, especially on this tablet. But anyway, so you understand that this is a circle, okay, that I've drawn, and this radius is r. Okay, so all these points which are within this circle, so this entire region here, okay, so which is within r from x. Okay, so that is the sphere or neighborhood around the point x dot. Okay, so this is for, you can define it for any r, for some radius, there is some radius r, and that's how you define. Now a set is open if around any point in that set you can draw the sphere which is completely contained in omega. Okay, so let's take an example. So suppose you have a set like this. Okay, is this going to be open? So you need to check that around every point in this set. So the set is basically everything inside this polygon. Okay, so this is the whole set omega. Now, is this going to be an open set? You need to check that around every point here, there's a sphere of some radius which is completely inside omega. Right? So if you take a point here, yes, there is something, you can construct a sphere like this, which is completely inside. So similarly here, you can construct. But if you take a point here, for instance, any sphere you take, there'll be some part which goes out of this polygon, right? So this, yeah, so So then you have some points which, for which you cannot construct a sphere of any radius, which is completely in omega. So this is not open. Okay. Okay. So now, so is this idea clear, like what we mean by open set? Any questions? Okay. Okay. All right. So let's just see. What about this set 0, 1? So I'm considering everything. I mean, the set of all numbers. Okay, it's just on the real line. I'm just looking at this interval 0, 1. So is this an open set? So this does not include the points 0 and 1. Okay. So.
Yes, ma'am.
Okay. So you're saying this is an open set, right? Okay, so this is without these endpoints 0, 1. So any point here you take, you can construct a sphere. So this is a real line. So the notion of sphere here is just that you should have x minus x naught. So it's just the absolute value should be less than some r. Okay, so it's just on this one dimension. So that you can do at every point, right? At some point here, you can construct a very small region around this, okay, which is completely contained. So that's why this is an open set. Now, the moment you include its endpoints, so if you include these points, 0 and 1, okay, it fails to be an open set. Can somebody tell me why? Do you understand why?
It can't find any like x naught at 0 and 1 point.
Okay, you take 0, then you cannot find a neighborhood around it which is completely contained, right? Because there'll be something which comes to this part. When you take the absolute value, you'll find something here which comes out of this interval. Okay, right. So that's the same thing. So now what about this set? Norm of x1 plus x2, it's strictly less than 1. So this is all points in the R2. So you remember, like we had plotted this in the past. So it looked like something like this, right? You had 1, minus 1, and this is 1, and this is minus 1, and something of this form. So this is what this norm, this is the contour of the norm where it is equal to 1. So this thing is the set of all points such that the one norm is exactly equal to 1. Okay. Now, if you look at, let me use something else to make it clear. So the region that you're looking at is something inside. Okay. And it does not include these boundary points because it is strictly less than 1 that you're considering. Okay. So is this an open set?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, good. So this is open. Okay. But the moment you start saying, when you say that x1 plus x2, if it is less than or equal to 1, so if it includes this line, then it does not become open anymore. Okay. So fine. So now let's go to what is called the limit point of a set. So a lot of limits everywhere, but you will see that they're all like very similar. The idea is very similar in the sense that a point x, you say that it's a limit point of a set omega if you have a sequence that converges to x. Okay, so what it means is that you can approach this point x in some way, okay, from the set. So that is what is a limit point. Okay, so let's just see an example. So now again coming to this this interval 0, 1. Okay, so again you have 0 and this is 1. Okay, this is the real line. So what are the limit points of this set? So to do that,
0 and 1.
So 0 and 1. Okay. So what about, so yeah, Correct. 0 and 1 are limit points. Now, is there anything else? What about a point like this? Suppose you have 0.5. Is that a limit point of the set?
Yes, ma'am.
Yes. So 0.5 is also a limit point. So why? Because you can have a sequence. You can have a sequence like this, right? Which comes slowly and approaches 0.5. Okay. And what about 0.25? Is this point 0.25? Is that a limit point? Yes. Okay. So by the same reasoning, right? So actually for this set, you take every point here. This whole set is the limit point. I mean, are the limit points. Okay. So let me just write that. So the limit points here is the entire set itself. Okay. So the limit points here is the interval 0, 1 itself. Now what about this open interval 0, 1? So what are the limit points there?
Ma'am, close
Everything
0 to
except
1.
0, 1.
Ma'am, including 0 and 1.
Including 0 and 1. So here the limit points are the same thing, right? So somehow my handwriting is becoming very bad today. Okay, so the limit points are 0, 1, the entire set 0, 1. So why is that? Why is 0 a limit point for this set? So everything else inside is okay. What about the 0? 0 is not part of the set.
We can still approach 0. According to the definition, if we can approach, then we can say that it's a limit point.
It's a limit point, exactly. So you can construct a sequence within omega, within the set, which approaches 0. Even though you don't touch 0, you can still approach it. So that's why these are also limit points. Now, what about this set? This omega is a set of all x with norm less than 2, excluding the point 0. Right? So if it's in 2 dimensions, suppose, so then you're going to have this, right? You're going to have the radius of this is 2, but this point x is 0 is not there. Everything else is part of the set. So what is the limit points of this? And even the boundaries are also there. So what is the limit point of this set? This point is not in omega.
Shouldn't the graphs just be the open interval, the closed interval minus 2 to 2? Right? This is certain.
For this one, so here, okay, I'm just taking everything in R2. Okay, so this is like in 2 dimensions. So the norm consists of everything which is inside. So this set x less than 2 is everything within this circle, right? And out of this, I'm excluding this point, the 0, 0 point. Okay, so yeah, is that answered? Like, what do we? Was your question answered?
Yes, ma'am.
Was Rohit, right? Yeah. Okay. So what are going to be the limit points of this set?
All the points in the circle.
All the points inside, right? So everything, even including the 0. Okay. So yeah. So these are some ways in which you have to understand the geometry of the set when you try to find the limit points. Okay. So that if you sometimes if just by applying definitions things become hard, but once you see the geometry, immediately you know what's going on. Okay? So now, yes.
Can you give an example where the limit point is not the whole set?
So where the limit point is not the whole set, so even this one, right? I mean, you have something else outside.
Yeah, no, ma'am. That was understandable, but like not all the there's some significant part of the set which is not the limit point.
0 to 1, 2 to 3, then 1.5 is not a part of that set.
0 to 1?
2 to 3, union 2 to 3.
So this is, you are writing the closed or open interval?
Either way, closed or open.
Okay, let's take it open. 0, 1. Union
2, 3,
2,
closed
3.
interval, open interval or closed interval, yes. Then 1.5 is not approachable. Right?
Yeah, but
Something like
1.5 is not in this set, right? Anyway. So I think his
oh,
question was something in which you have some elements of the set which are left out from the limit point.
Yes, ma'am. What would be that kind of a geometry I just wanted an example.
So one thing you can have is the set of all integers, right? So if you have something like set of all integers, yeah. So like 1, 2, 3, and so on. Okay. So here, is this going to be, what are the limit points of this set?
Ma'am, still the entire set itself because of constant sequences.
Because of constant sequences, right?
So, ma'am, it's not possible then.
Right.
What's it that is
So,
asking?
yeah, this is actually a good question. Yeah, perhaps it's not possible if you'll have those elements in the set which will be limit points themselves. But the question is whether you have something more or not, right? Yeah. So I guess that's the way to look at it, right? Yeah, because anything you have in the set, you'll always be able to approach it using constant sequences, as you said. Okay. Right. So that's a good question. So who asked that? Siddharth, right?
Yes, ma'am.
Siddharth. Okay. Yeah. So now coming to closed sets. So closed sets are those sets for which, every point, the set of all limit points is exactly the entire set. Okay. So every limit point lies in that set. So all these points, 0, 1 is closed. This closed interval, that is a closed set. Now this is not a closed set. This open 0 and closed 1. Okay. Because 0 is also a limit point of this set, but it's not part of the set. Okay. So is this an open set?
No, ma'am.
It's not an open set, right? Because you have this point 1 around which you cannot draw a neighborhood which is completely contained. So what I want to highlight here is it doesn't mean that open and closed, they're not like opposites of each other. Okay, so if it is open, it's not closed. If it's closed, it's not open. That's not the idea. Okay, they're two different notions themselves. For some reason, it's named this way. Okay, so yeah, don't get confused because of the naming methodology. Okay, so now coming to interior of a set. So the interior is, intuitively you can think of it as everything other than the boundary. So it's to write it in terms of these topology notions. What you do is you just say it's the largest open set that you can contain in the set. Okay, so that's the interior. Now, coming to boundedness. So far what we saw is sets, about some properties of sets. So these things are useful because finally, when you approach an optimization problem, you're going to have a constraint set. Okay, you're going to have a set of points from which you're going to look at the possible solutions. Okay, so that's why it's important to understand these notions of topology, or the geometry of the set. Okay, now coming to functions. So we have this notion of bounded and unbounded functions. So that's what we'll see now. So function is bounded if you can have some upper bound for it. So that's when you say it's a bound. The function is bounded above. Okay. So you can find some m such that f of x is less than or equal to m for every x in the set. Okay. Now similarly, bounded below is if you have f of x is greater than or equal to m for every x. So, so let's just go over some examples. So f of x is x squared, okay, and I'm taking the whole real line. So is this a bounded function? Okay, is this bounded above?
No, ma'am. It's bounded below.
Yeah, right. It's not bounded above. Not bounded above, but it's bounded below. Okay, so the bound, what is the lower bound here? what is the value of m such that this is f of x is greater than or equal to m?
Zero.
0, right? X square is always going to be greater than 0. So fine. So what about this function e power minus x, and I'm defining it on all the positive or non-negative numbers. So is this bounded?
Yes, ma'am. It's both upper and lower bounded.
Okay, so can you tell me an upper bound?
1,
Okay,
and lower bound would be 0.
upper bound is 0. Upper bound is 1, sorry, and lower bound is 0. Okay, so if I take it as if the domain omega is R, not R plus, then you won't have this property, right? It won't be bounded, right? Okay, so yeah, so you will still have the lower bound as 0, but the upper bound will not exist then. Okay, so now what about this function sin x? Can define and taking it over all of R. So what happens to this? Is this bounded? Is this unbounded?
Plus minus 1.
Plus or minus 1, right? So plus 1 and minus 1. So this is a bounded function. So you can see that, this notion of boundedness, I mean, it's about the function. I mean, sometimes it also depends on the domain that you consider. For example, in this case, the second case, omega is R plus, you had both cases were bounded, but when you consider the whole space, okay, all of R, then you didn't have an upper bound. Okay, but here you have this thing where you consider the whole space, but still the function is bounded. So it's kind of a combination of both the domain as well as the function itself. Okay. So now this is about boundedness of functions. Now, when you come to sets, when is a set bounded? And for that, you'll make use of this notion of norm. So you'll consider the norm function, and that has to be bounded. Okay, that's when you say the set is bounded. So norm of every point in that set has to be bounded. Okay, now here doesn't matter which which norm you consider. You can consider 1 norm, 2 norm, or any of the norms because they're in some sense equivalent. So if this property holds for one norm, it will also hold for any other norm you take. Okay, so this property, what it's saying is that you can fit the set inside a big ball. Okay, that's what this property means when you say the set is bounded. Okay, so basically you can enclose it in a ball of some finite radius. That's critical. Okay, so yeah, these are things we saw about upper bound. So you know what an upper bound is. Now the least upper bound is the lowest value among all the valid upper bounds. Okay, so there is this notion that I want to highlight between supremum and maximum. Okay, so many times you will have functions like every of these functions, whatever functions you take, you're going to have some upper bounds, right? You will always be able to find some largest value of that or something which is greater than that, provided it doesn't go to infinity. Okay, so if you have that, then you can always define a least upper bound. Okay, so that is what is called supremum. But maximum is when you have the set omega, right? So the largest value, an upper bound that exists within omega, that is the maximum value. Okay, so that's the subtle difference between these two. And similarly, you have these things about lower bound. Okay, so for lower bound, you can define what is called the greatest lower bound or infimum. Okay, so it's analogous notions. So let's just see these examples. So this is something which we also saw earlier. So for this problem, minimize f of x such that x is in this open interval 5 infinity. So for this problem, what are the lower bounds? So lower bounds are basically all of these, right? Anything less than 5, right? So 5, 4, 3. All these are lower bounds, right? And the greatest of this is 5. Okay, so that's what is the infimum, that is 5. But if you take the minimum, there is no point in the in the set omega which is lower than everything else in the set. Okay, so 5 is the infimum, but that doesn't belong to the set. Now, if you take 5.01, okay, is that going to be a minimum?
No, ma'am.
That's not right. So you can find something always less than this. So you can find 5.001 and so on. So there is no minimum for this set, but infimum exists, and infimum is 5. Okay, so you can define the analogous things for these other examples for supremum. So for this example, you have supremum is so f of x is x, and from n is infinity to 5. For supremum is 5, but there is no maximum. Okay, no max. So similarly here, there is no minimum. Okay, so this is some things about boundedness of functions. Now, as a last thing I wanted to do was continuity. So continuity of functions. So when you say a function is continuous, so it's continuous at a point x naught. If you take every epsilon, okay, in the function space, then you can find some delta, some region around x naught, such that whenever x is within some delta of x naught, f of x is within epsilon of f of x naught. Okay, so I mean, it's just yeah, the math is, sometimes you wonder why it's defined in this way, but it's just to say that as you approach x naught in limit, you will reach f of x naught. Okay, so there'll always be a region around x naught. For any errors you take in the f, there'll be a region around x naught where you are very close to f of x naught in terms of the function. Okay, so and you say a function is continuous if it is continuous at all points in the domain. Okay, so so all these, if to come up with examples, all these polynomials, right, x squared, and in fact any polynomial take, it's going to be continuous. So discontinuous function, an example is what I've constructed here. So say f of x is 1 by x minus 2 when x is not 2, and it is 0 if x is equal to 2. Okay, so the function looks like something like this. So at the point 0, so this is a point 0, and then the function value is minus half, and it keeps going lower and lower, and it keeps going it goes very down in the negative sense, it goes very large. And for anything greater than 2, okay, so if you take x is 3, right, so you'll get the value 1. Okay, and anything else, you'll have something of this form. It grows very large in the positive sense. So at the point 2, the function value is 0. So here there's a discontinuity at the point 2, right? Because anything you take around this point, okay, you are very far from the function value at 2. Okay, so in both cases, so that you should verify that this is true. This property, right? For all epsilon, there is a delta. So let's just fix epsilon as 0.5. Okay, so I'm taking, so that's in the function space. I have this range here, right? Like between, yeah, so this is epsilon. So this is 0.5. Okay, now if I want the function value to be within 0.5, I cannot find some x here. Okay, so that's the whole idea. So you cannot find a delta for which whenever x is within delta of 2, the function value is within 0.5 of this. Such a thing you cannot find. So yeah, that's this notion of discontinuity. Okay, so in optimization, all these notions are important because one theorem due to Weierstrass is that when you have a closed bounded function, closed bounded set, okay, and it's a function from omega to r, and the set omega is closed bounded, and the function is continuous. Okay, the function that you define is continuous. Then for such functions defined in this manner, there will always be an optimum point. So there will always be a minima and also a maximum. So that's why these notions are important here. And generally, you'll see like the topology and some properties of functions will prove to be very useful when you later discuss, when you see optimization problems. Okay, so I think I'm out of time, but yeah, I think this completes the prerequisite part for this course. So from tomorrow, we'll be going into more details on optimization and unconstrained optimization. Okay, so any questions so far? All good?
Can you go back to the screen for a second?
Yeah. Yes.
Never mind. Thank you.
Okay, so yeah, if there are no questions, so we're done for today. Okay, so thanks a lot for coming, and so I'll see you guys tomorrow at 2. Okay.
Thank you, ma'am.
Yeah, thanks.
Thank you, ma'am.
Thank you, ma'am.